In this video, we're going to talk about telescoping series. So a telescoping series is a series that has a bunch of internal cancellation when you add up terms. And when that happens, I'm able to easily test to see if it converges or not. So I want to get right into this by doing an example. So I want to determine if this series converges or diverges. And if it converges, find the sum. So I got the sum from 1 to infinity of 1 over n times n plus 1. So the first thing I want to notice is if I were to plug in terms into this, so if I plug in 1, I get 1 over 1 times 2, which is 2. If I plug in 2, I get 1 over 2 times 3, which is 6. If I plug in 3, I'll get 1 over 12, and then I get 1 over 20, and I could keep going like this. But when I look at this, it turns out it's not geometric. There isn't just a common ratio I keep multiplying by every single time. And there isn't really, initially, it doesn't seem to be a nice way of figuring out what it adds up to. But there's this trick I can use from Math 12, from Calculus Part 2, which is this type of thing, I can decompose it using partial fractions. So partial fractions are coming back here. I need some partial fractions. So I'm going to take this fraction that I have, 1 over n times n plus 1, and I'm going to split it into two fractions. One that has this first factor n on the bottom, and another one that has that second factor n plus 1 on the bottom. And then on the numerator, well, the degree of both of these polynomials is 1. So the numerator's got to be something of degree less than 1. So degree 0 polynomial, which is just a constant. And I'm going to call that constant a. Similarly, this numerator would also be a constant. I'm going to call that b. And I have to figure out what a and b are. And there's a couple of ways to do this. But the way that I like doing it is, let's first clear all the denominators. So I can do that by multiplying both sides by all the factors, n times n plus 1. Same thing on this side. Multiply by n times n plus 1. And then on the left-hand side, I'll be left with 1. On the right side, I got to take this whole thing, distribute it to each of these. That'll leave me with a times n plus 1, and then plus b times n. All right, so looking a little nicer. And the key thing about this is, well, this needs to be true no matter what value of n that I pick. So now let's plug in some nice values for n. So plug in some nice, I'll put this in quotes, some nice values for n. Okay, so what are some nice values? I noticed that if I pick n equals -1, this part just becomes 0. So that one's nice. I'll plug in n equals -1. And if I plug that in, I get 1 equals 0, and then minus b. Oh, so that means b equals -1. So I got b. What's another nice value? Well, if I plug in 0, this part becomes 0, so that one's also good. And generally, you want to pick values for n that'll make some of the factors be 0. So if I plug in 0, I'll get 1 equals a, and then plus 0. Oh, that means a is just 1. Okay, so I got a, I got b. Now I'm going to plug them back into this original setup here. So when I do that, when I plug in for what a is, and when I plug in for what b is, it's going to turn this fraction into, I get 1 over n, and then I get -1 over n plus 1. So I end up with this. All right. So, well, how does this help me? What I'm going to do to figure out what this infinite sum is, let's just look at a partial sum first. Let's just say I'm adding up m of these. So if I start off by plugging 1 into this, I'll get first 1 minus 1/2. If I plug in n equals 2, I'd get 1/2 minus 1/3. Then if I keep going, I get 1/3 minus 1/4. If I keep going, eventually the last one would be 1 over m minus 1 over m plus 1. And then the one before that would be this. And then there's something really nice that happens here. I want to give you a quick 30 seconds to pause and see if you can figure out what's the really nice thing that happens with this. In 3, 2, 1, pause it and try that. Okay, so hopefully you did that. The really nice thing is there's a bunch of cancellation. Minus 1/2, positive 1/2. -1/3, positive 1/3. There's a negative and a positive 1/4 here. This 1 over m minus 1 will cancel with the negative version of that before. and the negative 1 over m and the positive 1 over m cancel. In fact, all that survives is there's this 1 at the front, and then minus 1 over m plus 1 at the end. So what that means is that sum of the first m terms ends up just being this. And now I just got to take the limit of that. So now I just got to do the limit as m approaches infinity of this 1 minus 1 over m plus 1. So when I do that limit, well, the 1 just stays there. And then I get 1 over infinity, which is 0. Oh, that's just 1. That is just 1. So this kind of bizarre looking sum of fractions ends up just being 1, but doing the partial fractions made it so much easier for me because I got a bunch of cancellation, and then it gave me something that I could just take the limit of to work out what it ends up equaling.